Okay, well, happy Monday, everybody. It's week 7, and so we're moving right along, and we only have a few weeks left in the quarter. I don't know how you guys are doing. I feel like I'm looking forward to summer. So, um, I mean, I still love my job. I still love teaching and everything, but I definitely feel like I could use a break. So anyway, and I say this as we're in week 7, and I'm going to give you guys a midterm exam on Wednesday, and you have to study. So, um, but yeah, I, I understand it's been rough. We've been doing online learning for a long time, and uh, I hope you guys are doing okay. Um, all right. Uh, let's bring up our next topic. Again, so this is I'm going to introduce support vector machines, and this topic it's a bit like we'll discuss it, but the way it works is still a bit of a bit of a mystery, and even if we understand kind of conceptually what's happening, when we apply it in real life, sometimes we just kind of tweak some parameters, and we're hoping it's able to find some kind of um, partition that separates different classes and things like that. So this is a topic that we'll take a look at. It is not going to be covered on the midterm exam. It is covered a little bit in the homework that I've assigned this week, and you'll kind of like look at the pictures, and you'll try to understand what these different parameters mean from the pictures. And I'll talk a little bit about it in today's lecture as well. I have a feeling I will not get through all of the slides today, and so I will have to continue this lecture, the same set of slides on Friday. But we'll go ahead and introduce the topic here. Okay, so support vector machines is a classification method, and we're going to start by looking at the simplest version of the support vector machine, which is called the maximum margin linear SVM. Okay, and so we'll introduce the linear SVM, and it only works when the data is linearly separable. Okay, and we'll start there, and then we will slowly kind of modify this to make it a little bit more complicated. We'll move into like the soft margin SVM, and then we'll do what's known as the kind of the kernel trick to kind of deal with data that's not linearly separable. But we'll start here, okay? And so the idea here is that we are going to find parallel hyperplanes. If all of my examples will be two-dimensional, and so a hyperplane in 2D is just a line, okay? But you can imagine data that exists in higher dimensions. So if it's in 3D, you're looking for basically a plane in 3D space that will separate our data. And if it's in higher dimensional things, then you have this hyperplane, which we can't really visualize, but it's the same idea as kind of a straight line or a flat surface, but just in higher dimensional space. And basically what we want to do is we want to be able to separate the two classes from each other. And we have to find two hyperplanes where the distance between the hyperplanes are, in 2D, we're going to find two lines, two parallel lines, and we want the distance between the lines as wide as possible, okay? And so I'm going to show a bunch of slides, and basically we'll have a few examples of just different hyperplanes that all work as a boundary that separates the data, but we're going to pick the pair of lines that have the widest distance between them, and that's going to be the maximum margin boundary, or the maximum margin linear SVM boundary here, okay? So here we're going to have two classes of data. We've got the blue data and the red data. And so we can draw, there's lines that we can write, I can draw a straight line here. And there's, infinitely many of them that I can draw that will separate the blue and the red, okay? So because our data is linearly separable, right? So here's one example where we will have 100% correct classification. So here, if I draw a line, the dotted line is going to be one hyperplane, and the other dotted line is the other hyperplane, and it separates. On one side is all the red, and the other side is all the blue. But the margin between these two lines isn't super wide. Okay, the line in the middle is kind of just the mean, or the line in the center between the two dotted lines. But when we're talking about a hyperplane that separates them, these are basically what we have, two things, right? And so here I can draw like several hyperplanes, and if I change the angle, we can see that the margin between them gets wider and wider, right? So as I kind of make these, they get wider and wider. When the so at least at this angle, this is the widest I can go. And here I've kind of circled the points that the line intersects, right? I can't. So if imagine a point centered at each of these plus or minus signs. If I move this dotted line, kind of further away, then this this red minus, the center of the red minus, will end up on the wrong side of this line, the hyperplane here. Okay, and same thing here. So these almost kind of act as like guardrails as far as how where the lines can be drawn. Okay, and so here we get a pretty wide margin here, and we actually get the margin to be even wider if if I angle this. This no longer acts as kind of the boundary, one of the boundary points, or technically it's the support vector. It's not going to be one of the points that separate it, but it's going to end up being these 2 points, and then this one. These three end up forming kind of defining where the three widest, or the 3 points that create the widest margin. Okay, and I can keep drawing. There's other hyperplanes that I can draw, like this one is also 2 lines that are separated, and this one runs into here, and they're separated, and I can keep making it like this, but at this point the margin between them is quite narrow, right? So this is kind of just a selection of some points or some possible boundaries that I can draw that will still have 100% separation between the blue and the red. And the way we are going to work is we're going to say this is the best one because the margin between blue and red is wide as possible. Now, is this the best? I don't know. Okay, I don't know if this is actually the actual best, but as far as how we've defined how we're going to select our boundary, we're saying we want the one where the margin between them is as wide as possible. Okay, we just don't have a whole lot of data over here, so we don't really know, right? Like if we know that there's red points over here, then we'd say, oh yeah, this is good. Okay, but it could turn out like if later on a blue dot shows up over here, then this will be the better boundary, right? But we actually have nothing up here. This is this unknown region, so we don't really know if this corner, should this corner be red or blue? We don't really know. And so just based on the data that we've seen here, so if there's a red or blue dot here, that's going to definitely affect things. But based on what we've seen here, we're going to just say, okay, the one with the widest margin, this is the one we're going to pick. Okay, and again, a lot depends on what data you have. All right, so so what hyperplane are we going to pick? We're going to pick the one that maximizes the margin, and again, the margin is the distance between the kind of the perpendicular distance from the decision boundary to kind of the closest points to either side. So we look at this, the line in the middle. This is going to be kind of our decision boundary, and we say, all right, how far perpendicular? What's the perpendicular distance from this line to this dot and the perpendicular distance from this line to this dot. That's our margin. We want that to be as wide as possible. And what happens is that decision boundary is defined really only by these 3 points, this point, this point, and this point. I could add a whole bunch of blue dots over here. I can add a whole bunch of red dots over here. And as long as I don't kind of enter inside this margin zone, I am not going to change the addition or subtraction of red dots on this side, or the addition of subtraction of blue dots over on this side is not going to change the location of this boundary, okay? And so these 3 dots, which define the boundary, these are known as the support vectors, because you can think of the dots or the points in space as vector locations. And, you know, kind of when you add them together, you take the, you know, you do some kind of operation with them, you can get the line that defines this. And those 3 locations, those 3 points are the support vectors, as in this boundary is entirely defined by their values, okay? So you can change the location of the other data points, and the location of the boundary will be unaffected as long as the support vectors remain the closest points to the boundary, right? So as long as you don't put any point that's closer to the boundary than these 3 points, this will be the boundary. Okay, and so just to kind of describe this is what our picture looks like. This is the margin. It's the perpendicular distance between these 2 dotted lines, and this is the largest distance that we can get. All right, let me go ahead and give you your first view quiz answer. First view quiz answer for today is A. A as an apple. A as an apple is your first view quiz answer. Okay, so so here are our support vectors. This is the margin. It's going to be as wide as we can have. Again, if we picked different support vectors, all right, and we said, all right, you know, I want this point and this point, you know, the margin here is a lot smaller, right? And so this is not going to be the boundary that we choose. Okay, so how are we going to maximize this mathematically? All right. What we're looking at is, you know, we have this training data. Basically, the red dots and the blue dots form our training data. Okay, and what we're going to do is we're going to label them as either +1 or -1, and that's why I have red and blue has plus signs, and then the red dots over here are minus signs. Okay, because this is how we're going to label our training data. Is you know, you have your x coordinates. Okay, so x being a coordinate, at least in our example, a 2-dimensional coordinate, and then t being the label, and the label is either +1 or -1. Okay, and what we're going to do is we're going to try to find this maximum margin SVM, which is going to be, you know, some boundary that divides the 2. Okay, and basically this line that goes in the middle here, okay, this can be defined by some hyperplane where W, okay, so we're looking for the set of points x. Sorry, we're looking for the points x that lie along this line, such that when I multiply W times x, okay, some vector W times x, and subtract off some constant, it's going to be equal to, you know, basically 0. Okay, so basically, this is how we're going to define our line. Okay, so this is basically, you can think of this almost like you've got this this vector W, which is perpendicular to this plane here, and when you take kind of your x1 and x2 coordinates and you multiply W by x1 and x2, you know, it's going to form a constant, and you're basically finding all the points where W times X1 and X2 add to some constant, okay? That constant being B, and you can kind of rearrange things so that W transpose X minus B is equal to 0, right? And so that boundary is going to be the set of all points where, W times X1 and X2 add to some constant. And then if you have values on one side, that's going to be the positive side of the margin, and then values on the other side will be the negative side of the margin. Okay, so you have kind of parallel hyperplanes, which will be W times your vector W. Basically, you've got to, if X is in 2 dimensions, X1 and X2, you've got W1 and W2, W1 X1 plus W2 X2, those add up to some constant, and we're going to say on one side we're going to have W transpose X minus B is equal to 1, W transpose X minus B equal to -1 for the other side, the negative side of the margin. The set of all points X that satisfy this equation, the set of all points X that satisfy this equation are going to be parallel to the set of all points X that satisfy this equation. So whatever X satisfies this equation, if you basically just create a, find another parallel line, they're going to satisfy these things, okay? And what we're going to do is we're going to let X1 and X2 kind of be the closest points from each class, right? And they're going to lie on the edges of the margin, right? So this is me kind of labeling all of these things, right? So here you have all the points X, right? Where you have W transpose X plus B equal to, to 0, and then all the points X that satisfy this, W transpose X plus B equal to -1 will be, will form this boundary over here, and W transpose X plus B equal to +1 will form this boundary over here, right? And if some new point is on the boundary itself, this is going to equal 0, right? So is this going to be better if I do an example with just some numbers here, right? So here we've got X1 and X2. Let's say we have 0 and 0, okay? And then let's say, just for simplicity, let's say W1 X1 plus W2 X2 plus B equals 0. All right, and so let's just do W1 equal to 1, W2 equal to 2, and B equal to, well, let's just plug in some numbers. Okay, so let's say I pick this point. So X1 is 1, and X2 is 2, 7. Okay, plus B. All right, so let's say B is equal to negative. Is that right? 7. Okay, and then so if I plug in 2 for X1, I've got 2 plus something. Actually, let's go over to 3, 2. Is this going to be right? And then, and I think we will get, basically, this is going to be our boundary here, right? So if I plug in, if X1 equals 1 and X2 equals 3, so then if I plug in 1 times 1 plus 2 times 3 minus 7, that should equal 0, right? And over here, I've got X1 equal to 3, X2 equal to 2. So I've got 1 times 3 plus W2 being 2 times 2 minus 7, that equals 0. And basically we're gonna form some kind of line here, right? And I can have x1 equal to 5, x2 equal to 1, 1 times 5 plus 2 times 1 minus 7 equal to 0. Okay, and then and if I say b equals, if we want parallel lines, we will have one that's basically here. And then we can have another parallel line here, where this is going to be W transpose X plus B equal to 1. And here I got W transpose X plus B equal to -1. Is that okay? I don't know if that's helpful as far as having like an example here, right? So if you define, if you've got some values for W1 and W2, okay, and so W1 and W2, if you think of like 1, 2, this is going to form a vector. 1, 2. 1, 2 is going to be perpendicular to the to this. Did I do plus B or minus B? Oh, I got minus B. Okay. But then in the picture I have plus B. I've confused myself. Okay. Yeah, it is a constant. So whether we're doing plus or minus, technically it doesn't matter. But yeah, I've got W transpose X minus B. I should have done. It's some constant here. That's a good catch. And so yeah, whether I've done, yeah, basically some arbitrary constant, maybe positive, maybe negative. And I apologize for the inconsistency as far as what I have in these diagrams here. W transpose X minus B or W transpose X plus B. But basically we've got some kind of constant here so that we've got this thing, right? And then basically the vector defined by W is going to be perpendicular to the to this line here. That's just kind of a I don't know, you know, a property of the thing. Okay, and so so here, what we have is we are going to take the margin is going to be the distance between 2 points that lie on the boundary, right? So here I've got, I'm going to just define, you know, here's 1 point that lies on this line, and we'll call that x1. And then, and this point over here, it will be x2. And so the vector x1 minus x2 is going to be basically the arrow that connects these 2 points. And then if we take the dot product between x1 and x2, and we take the dot product onto this vector w, right? So here's my vector w, and if I take you know, some point here and some point over here, and I've got, you know, I've got a vector that connects these. This is the vector x1 minus x2. You know, this is confusing because I have the, this is, I'm going to call this xa minus the vector xb, right? So this is, we'll call this a and b. And if we dot that with this directional vector w, okay, then we would get the margin. That's what this diagram is, right? So this arrow is parallel to whatever, you know, the vector w. The vector w is perpendicular to this boundary. And then if we take the dot product between one vector and another vector, you will get the projection of that vector onto that direction of the other vector, yeah? Okay, so so this is what we're doing. We got x1 and x2. They're points closest from the things, and with the way our boundary is defined, what we're going to say is that a unit vector perpendicular to the boundary is going to be w over the norm of w. Okay, so w is a vector perpendicular to that boundary, and we're going to kind of take that vector x1, x2, and basically take the dot product, or I'm going to just take do w transpose x1 minus x2, and that will kind of give me the distance of this margin, right? So I take this vector and I dot it onto the vector in this direction, and I'll get, basically the distance in this direction. And we're going to just define this distance as 2 gamma. We're going to say the distance from this side to this side is going to be 2 gamma, and we want this distance 2 gamma to be as wide as possible. So far, so good. Is that okay? All right, let me give you the next view quiz answer. Next view quiz answer is D. D as in dog. D as in dog is our next view quiz answer. Okay, so we will say we got W transpose X minus B equal to 1, and W transpose X, W transpose times X2 minus B equal to -1. And so we've got X1 and X2. We're going to replace those with basically, we're going to, when I multiply W transpose times X1 and W transpose times X2, okay, I'm basically going to take this, right? And here I can distribute the W transposes here. I can basically subtract a B and add a B. Okay, and that this thing will be replaced with a 1, and this will be replaced with a -1. And so I've got a 1 plus 1, and that's going to eliminate. We can cancel the 2 over here with this 2 over here, and we're going to just say, okay, gamma is going to be 1 over the norm of W. All right, so how do we now we want to maximize this distance gamma, and that's going to be equivalent to minimizing the norm of W. Right, so we want to minimize whatever, the norm of W, right? But we have this rule, we have this constraint that says whatever W we pick, it's got to be such that W transpose X minus B, X minus B is going to be greater than 1 for all of the objects that are labeled 1. And this statement, W transpose X minus B, has to be -1 or less than or equal to -1 for all of the objects labeled -1. So if we go back to this picture, we're like, okay, well, let's just pick the W's that's going to, have the smallest norm. But if I do that, I have to make sure that the result is still going to correctly classify all of these things to be positive and all of these things to be negative on this side. Okay. Because as soon as we do this, like all kind of references to X1 and X2 are gone. So we have to kind of keep that constraint, okay? And so, a clever way to kind of keep that is that, well, all of the T's here are going to be positive and all of the T's on this side are going to be negative. And so we can just kind of say that, whatever this, because this thing is going to have some sign, and we're going to say that, the sign times the sign has to be positive, greater than or equal to 1, right? Because when the label is -1, this thing's going to end up being, we're saying this thing has to be negative, and so that's going to negative times negative ends up being positive, right? So this is a kind of a clever way to summarize the constraint into one equation rather than having 2. Okay, and then once we get to that point, we're going to kind of take care of this using Lagrange multipliers, right? So we want to do this. And we get to a point where we're going to basically throw up our hands and just say, okay, we're going to let the computer do this. But I at least want us to get to that point, okay? So we want to minimize this quantity, the norm of W, and that's going to kind of be the same as minimizing this, right? So if we minimize this thing, it's also going to be equal to minimizing this. all right? And we have this constraint. And when you try to do optimization with a constraint, you can do Lagrange multipliers if you recall all of that stuff. And so what we're going to do is we're going to add a new term to whatever our objective function is, so that when we find the optimum of this function, it's going to be it's going to optimize the original thing, but according to the constraint. Okay, and so we have to do this. Basically, this constraint has, we're going to have a Lagrangian term basically for every single x in our data set. Okay, every single x in our data set is going to have some kind of Lagrangian term, because we got to do it for x1, we got to do it for x2, we got to do it for x3, all the way up through the nth term. Okay, and so you've got it, like, you're doing this constrained optimization, but you have to have all of these kind of Lagrangian terms inside there. So it gets a little bit messy. Okay, so you have this. Okay, this is going to be our objective function. We're going to say we want to minimize this. We want to find the W that's going to minimize the norm. Basically, this is the norm squared. So we want to minimize this. Analytically, it ends up being easier to minimize this thing. So that's W transpose W, and we're just multiplying it by 1/2 for, I guess it makes our calculations easier later. Okay, and then we have a whole bunch of Lagrangian terms, which is basically where this is the constraint that says all of the points have to be correctly classified still after whatever W you choose. So after whatever boundary vector that you choose, all of the points still have to be correctly classified as either being plus or minus. Okay, and here we have this this other constant alpha that just kind of, it needs to be positive so that we're not this is a thing that shows up with the Lagrange multipliers, but they have to be positive, right? We can't cheat and suddenly make them negative and things like that. Okay, so so we go through, and apparently this problem, once we get it into this form, we can solve it using quadratic programming. And I thought, well, you know what, let me dig into what exactly quadratic programming is and how it works. But everything I read, it was like a nightmare. So I still don't know how quadratic programming goes. Apparently R has a quadratic programming solver. I still don't know how to use it. I tried to read through the help. It was not very helpful for me. I don't know if anybody has done quadratic programming, but it was a bit of a mess. So I don't know, but this is how it gets. This is what our textbook says. Also, you look at the textbook and it says, okay, yeah, we don't know how to do this. There's no closed form solution, but quadratic programming can do it. And apparently it's a computational method, kind of this iterative thing, and it gets you to some kind of solution. So apparently once you get it into this form, we can arrive at a solution using computational power. Okay. Oh, I don't know why this slide is over here. This slide should have been earlier, where I'm just adding some random arbitrary minus signs and arbitrary plus signs into the thing, but the boundary hasn't changed. Okay, I messed up on the creation of this thing, but I put the slide in the wrong spot. But basically the support vectors, these are the support vectors, because I can add or subtract points and it's not going to change the boundary. Okay. Okay, and we'll go back to maximizing the margin here. And so we want to minimize this thing, okay? And we said we can do it with quadratic programming. And one thing to note is that at the minimum when we do this, the derivatives of the function with respect to W and B will be equal to 0, right? So when I take the derivative of this, right, when it's at the minimum, and you take it with respect to, how does this function change with respect to W, that it's not going to change, okay? And also at the minimum, this B term, when we change it, it's not going to kind of alter things either. And so, so we can say, you know, the derivative of this with respect to W is going to be when you take the derivative of W transpose W, 1/2, that's going to become W. And then all of these things, when you kind of multiply them all together, this is the only thing with the W term in there. So these will drop out, they're constants. But you take AN TN times XN multiplied by W, take the derivative of that with respect to W, you're going to get this summation here. So you're going to get kind of this term where the vector W is going to be equal to the summation of AN TN times XN, right? And then as far as the partial derivative with respect to B being the, you know, just that constant of kind of, you know, where this thing is kind of located, okay? That's going to be the summation of when you take it with respect to B, okay? It's when you multiply these terms out, AN times TN is going to multiply by this. This has no B term, so it becomes, it zeroes out. This has no B term, it zeroes out, but then we have a negative B here. And so, so we'll get that. This, you set that equal to 0, and we get this. Okay, so this is interesting to note, and this looks very scary. Okay, but it's actually not so awful if you'll just trust me on this. On this slide here. Okay, we can take this thing, so we have this vector W, and this vector W ends up being just the summation of some of the X values, okay? Some of the X values multiplied by some constants, alpha and T, okay? And so what I'm gonna do is we're gonna say, all right, you know what we're gonna do, take this thing where W is the sum of some X values times alpha and T, and we have W transpose W. And so here we have to kind of take the sum of all possible values of X, okay? And so I have two different subscripts. I have a subscript based on N and a subscript based on M. And that's just to kind of say, because here we're going to have a product of X times X, and we want basically every single possible product. So we're going to have basically N times N, big N times big N products of X transpose X along with the constants. Okay, so so we do that. We're also going to replace this W with this, okay, and to kind of distinguish it from the X's here, we're going to do this. All right, anyway, you go through this, you can follow this, you don't have to. It simplifies. A lot of these terms kind of cancel out when you take this full product and this full product over here. Some of the terms cancel out, and some of the terms do not cancel out. And what ends up remaining, okay, is that, so here we've got this multiplied by 1/2, and this one is not, and they end up combining, all right, and we get the sum of all of the alpha values, and we have this double sum of a bunch of alpha values across basically every possible X and every X in either kind of combination, right? And here we want to kind of find the optimum of this solution subject to this, all right? Again, no closed form solution, but it's done via quadratic programming, okay? But it's interesting to note that this solution isn't going to contain a reference to W itself, okay? It's just kind of a sum of all of these X terms. And so all to say is that if you find the W, all right, if you find kind of all of the alphas that equal here, you know, some of the alphas are going to end up equaling 0, okay? And the ones where alpha does not equal 0, those are going to be the support vectors, right? So depending on the X observation, some of the observations will have an influence on what W is, and the other observations are not, okay? So I guess kind of going back to this picture, these 3 points are really going to be the only points where alpha is equal to something. And then all of these points over here, because you have an alpha, kind of this Lagrangian term for every single observation, but for all of these observations that don't really matter as far as determining where the support, where this decision boundary is, the Lagrangian term, the alpha for all of those are going to be 0, okay? And the only ones that do determine the boundary are going to be these 3 points. Okay, so we can think of, you know, when you do kind of your optimization with kind of these Lagrange multipliers, you can think of whatever alpha you have as a measure of how much influence a particular value has in defining what the boundary is. Okay, and so identifying what the boundary is just comes down to a matter of identifying the correct correct kind of multiplier terms for each of the x values, right? And so if the x value, if that x location is not going to influence the boundary, its alpha term is going to be 0. And then if it influences the boundary heavily, you know, you're going to have some kind of constant here. Okay. So that if we solve this, that's going to figure out our maximum margin boundary. Okay. What we can do is we can kind of take this a little bit further, and we can relax one of these constraints. Okay. We said the boundary has to be greater than or equal to 1. What we can do is we can kind of relax that, and we can say, you know what, it's okay if the after we find the boundary, we multiply by x, you know what, it's okay if it ends up inside or on the wrong side of the boundary. Okay, and so this is, there's this just this xi value, okay, and xi can be anything greater than 0. It can be between 0 and 1, where you will allow for points to kind of ending up in the wrong, ending up within the margin, or here you can have xi even greater than 1, where points can end up on the wrong side of the boundary, right? So so kind of the picture here. Let's save this. The idea being, you know, we start off with some points, and so first we said, you know what, the boundary's got to be kind of like this, okay? Now what we can do is we can relax this, and we can say, you know what, we can actually have a different boundary, right? Maybe something like this, and we can actually draw the margins, you know, even a little bit wider or something. And you can actually have points that are inside the boundary. Okay, that's a possibility. That's what it means to have a soft margin. And so if you go through kind of the same process of trying to refactor the problem into this quadratic programming form, you can do this, and it ends up ending up kind of the same. But here, now we just have another constraint where we say, you know what, the alphas, the Lagrange, the kind of the multiplier constants here, they have to be less than some value c, okay? And this value c is just kind of a limit on how much influence any one point can have on the location of the boundary. So for example, if let me just let's say we have data that look like this. Okay, and it kind of makes sense for there to be a line that looks like that would look like that, right? That kind of makes sense for there to be a boundary here. But what could end up happening is, let's say one point. What if we get a point right here? Okay. So before, if this point was missing, okay. If this point was missing, we might pick a boundary that, how do I draw this? I think this boundary would make sense, okay? But if we include this point here, then the boundary that we have to draw is gonna have to be something like this. Let me see, it's kind of hard to, okay? We would have to draw this in order to kind of correctly classify things, because this point, if this, I don't know how to write this better, but I think this one makes more sense as far as where the blue and red points are. But with this one point here, we have to redraw the boundary. Okay. What a soft margin will say is, the soft margin will say, you know what, let's keep this one that quote makes more sense, and we will just allow a point to be on the wrong side. Okay, we'll allow one of these points to end up falling on the wrong side. And so, we're putting some kind of limit on how much influence a single point can have on defining the boundary. Okay, all right, let's hold off on looking at kernel functions. We'll do the kernel function transformation on Friday. So we'll end here for today. Let me give you your last view quiz answer. All right, and so our last view quiz answer for today is B. B as in bear. B as in bear is your last view quiz answer. Okay. And the I'll put this in the chat. Okay. All right. I know there was a lot of stuff with quadratic programming and kind of just refactoring things around and moving things around. I'm going to just say, don't worry too much about it. Okay. Just conceptually stick with the idea of having this line that we're trying to maximize the margin for. Okay. So we'll just keep it at this high level conceptual point, and I think that's okay. And then we'll look at kernel functions on Friday. Okay. Good luck as you guys study, and we will see you guys on Wednesday for the midterm exam. So good luck, and we'll see you guys then.